Hey, AP Chemistry, coming at you with the long-awaited FRQs that I assigned maybe a week and a half ago or so. Sorry about that. I'm just kind of hammered down here with a 2-year-old and everything. There's just a lot of stuff going on in life, but I'm sure all of you are having that situation as well. Regardless, the AP test is coming up on the 14th, and I hope that you are going to be prepared for that in the coming days. That's how long is that away? Goodness gracious! Let me look at my calendar here. So that is next week Thursday. Next week Thursday. A couple things. Double check that you are signed up on the College Board website and you're getting their emails. If you're not getting their emails right now, you need to make sure you have your email correctly set up. If not, that is a big deal. Double check your emails that you're getting the College Board website's emails from them. That is kind of the indicator. If you're not getting them, then you need to go fix your email, because all the links, all the information about the online test will be through the email you've given them. And that's coming up next week Thursday, so please email me questions, talk to me. I'll be available for office hours on Thursday at 10 to 11 a.m. I just got to do things early because life is crazy at the afternoon hours because the kid is taking a nap. But if you need me for anything at all, let me know and I'll be happy to help you out. I've put up one more practice test for this week to go over and just be prepared for next week's test. This week's test, practice test, is from 2017. It is the international test, so this is not really easily available. I was able to get it from their website, which is really cool. And this has different questions from 2017 than from the American test, essentially. So let's go through these questions here. I think this was from 2014. This was, I think, the international test actually from 2014. And these are some pretty good questions. Some of these questions are a little bit challenging, but they kind of feel challenging, but they're not that much really. And let me just double check. You can see that on the screen. Yep, looks good. Okay, so what I'm going to do is I'm just going to go through the key with you instead of trying to use the document camera. I felt like that was just really cumbersome, but the answers are here on the FRQs that I gave you in the PDF. Let's look at the first one you guys had a question about, and you guys had a question about every single one except number 3, I think. So let's just go through these. So we have a chart here. It's conductivity on the y-axis and volume of 0.1 molar sulfuric acid on the x-axis. It says a student performs an experiment in which the conductivity of a solution of barium hydroxide is monitored as the solution is titrated 0.1 molar sulfuric acid. The original volume of the barium hydroxide solution is 25 milliliters. A precipitate of barium sulfate, which has a KSP of 1 times 10 to the minus 10, formed during the titration. The data collected from the experiment are plotted in the graph above. Now, first thing with the graph here, this is kind of weird. It's conductivity. Now, something to remember is that conductivity is a measurement essentially of how many ions are dissolved in solution, because if you run a current through a solution that has ions, then that current can pass through. If there are no ions in solution, then that current does not pass through. And so they are measuring basically how many ions are in solution on the y-axis versus how much sulfuric acid they've added to it. And in a way, this is like a titration curve, but not quite the same, of course. But we can use, particularly this point right here, you can kind of think of that as the equivalence point for the amount of sulfate and barium that's being added, because those are the ions in solution which are affecting the conductivity. So it says, as the first 30 mils of 0.1 molar sulfuric acid are added to the barium hydroxide solution, 2 types of chemical reactions occur simultaneously. On the lines provided above or below, write the balanced net ionic equation for I and the neutralization reaction, and write the net ionic equations for, the equation for neutralization reaction and the equation for the precipitation reaction. So for the neutralization reaction, this is an acid-base reaction. You've got barium hydroxide and sulfuric acid. What is the neutralization reaction for that? It's right there. So like that. So H plus OH minus gives us water. And then the precipitation reaction that's taking place here. So we are forming, how do you know what's being formed? You know that from this, the KSP is this really tiny number. KSP, remember, is the equilibrium constant for the formation of a precipitate. If it's a really tiny number, that means you make a precipitate. So barium and sulfate sulfate is being added to the solution while barium is already there, so you're making barium sulfate. So the precipitation reaction is this one right here. You got Ba, 2 plus, reacting with sulfate to make barium sulfate as a solid. Okay. Part D, the conductivity of barium hydroxide solution decreases as the volume of sulfuric acid changes from 0 to 30 mils. Identify the chemical species that enable this solution to conduct electricity as the first 30 mils of 0.1 molar sulfuric acid are added. Okay, so this is the thing about what's happening. So you're adding in sulfuric acid, okay? So sulfuric acid is going in, so it means you are releasing H+ ions and sulfate ions, and in solution already are barium ions and hydroxide ions. So what ions are causing conductivity, or which ones are allowing for electricity to flow through as we are adding the 30 mils? Well, what ions are already there in solution that are causing conductivity before you even add the sulfuric acid? Well, you've got barium hydroxide in solution. So the ions that are making it possible for conductivity, barium 2+ or hydroxide. So that's really the answer right away. Before any sulfuric acid is added at all, there's conductivity, so it's got to be either the barium 2+ or the hydroxide ions. Either one of those is correct. And then the next question is, on the basis of the equations you wrote in part A, explain why the conductivity decreases. So looking at the reactions right here, as we're adding sulfuric acid, we're adding H+ ions, which react with hydroxide to make water, and pure water is not conductive for electricity. And then you're adding sulfate, which reacts with barium to precipitate barium sulfate. So you are taking away both of the ions which allow for conductivity. So that's the answer to part B there. So you're removing barium ions by making them, by turning them into barium sulfate or forming them with sulfate to make barium sulfate, and then the hydroxide ions are reacting with H+ from the sulfuric acid. You're making water. Okay, part C, using the information in the graph, calculate the molarity of the original barium hydroxide solution. So what we're going to do here is we're going to say, okay, well, this point right here, that's kind of the point where the amount of barium and the amount of sulfate from the sulfuric acid are equal to each other. That's sort of the point where the amount of barium that's reacting with sulfate, it's kind of reached the minimum amount there, and then at that point all you're adding is just more sulfuric acid. Okay, because as you add more sulfuric acid, the sulfate reacts with the barium, causing the barium ion concentration to go down. And then that's kind of your minimum point. You've taken all the barium out. And then at some point, you're just adding sulfate ions. And sulfate ions, of course, also are allowing for conductivity as well. So as you add more of them, then you're going to have your more conductive species or solution. So the part with C here is saying, okay, how can I find barium hydroxide's concentration? Well, at that point, that minimum point, the number of moles of barium hydroxide must equal the number of moles of sulfuric acid. We can kind of treat this as an equivalence point. And so the moles of sulfuric acid at that point will be equal to its concentration times how much you've added, 30 mils, so 0.003 moles of sulfuric acid. Therefore, it's a 1-to-1 reaction, so you have the same number of moles of barium hydroxide. And so we're just going to go ahead and do the calculation there. So 0.003 divided by 0.025 liters, so 0.12 molar is the concentration of the original barium hydroxide solution. Okay, part D, calculate the concentration of barium ions in the solution at the equivalence point after exactly 30 mils of 0.1 molar sulfuric acid are added. Okay, so we want to know how many barium ions are there in solution at that equivalence point. Well, at that equivalence point as well, the amount of sulfate and the amount of barium in solution are pretty much, they're equal to each other. They're equal to each other at the equivalence point. And so since we know that, we can use KSP to find the amount of barium that's in the solution as well at the point, since we know the sulfate at that point is equal to the barium. Okay, so since they're equal to each other, we can set that KSP value. We can use the KSP. So the concentration of barium times the sulfate concentration equals the KSP value. And since we know they're equal to each other, we'll just set them equal to x. And so we can solve for x. So x squared, and do all the math there. So we'll get this concentration, 1 times 10 to the minus 5th molar. Not too bad. But you're going to have to use the KSP to solve that there. Okay, next question, which I think is the last one. The concentration of barium ions in the solution decreases as the volume of added 0.1 molar sulfuric acid increases from 30 mils to 31. Okay, so they want you to explain why. Why is barium ions concentration going down still as we add in more sulfuric acid? Okay, and so this comes back to, this is a Le Chatelier's principle question. So they're asking, why is this continuing to go down as we are adding more sulfuric acid? This has to do with essentially a common ion effect. So as we are adding more sulfuric acid to the solution, okay, we're increasing the amount here. This is going down as well. The reason why it's going down, though, is that because we are increasing sulfate, we're causing the equilibrium on the right side. We're shifting the amount there. We're shifting it up. So this has to go down as well. So barium sulfate's got to go down as well. So it's got to go up. Okay, so if we're increasing the sulfate, we're shifting the reaction to the right. We're causing more sulfate to go up. Then barium sulfate, the solid, also has to increase in the amount that is there as well. We have to form more of it to reach equilibrium. So why is barium going down? Because it's got to be used to make more barium sulfate solid. Okay, and that's number 1. I'm going to take a quick pause here so I can get some water. Okay, back to this. And so we're looking at number 2. My child is running around doing crazy things. A student is given the task of determining the enthalpy of reaction for the reaction between hydrochloric acid and sodium hydroxide. The following materials are available. So we've got 1 and 2 molar hydrochloric acid, cups, thermometer, 1 and 2 molar sodium hydroxide, gloves, stirring rod, distilled water, goggles, and lab coat. The student may select from the glassware listed in the table below. So we've got 250 ml Erlenmeyer flasks, 100 milliliter beakers, 100 milliliter graduated cylinders with their precision given here: 25 mils for the Erlenmeyer flask, 10 mils for the beakers, and 0.1 mils for the graduated cylinder. It says the student selects 2 100 ml beakers, uses them to measure 50 mils each of 1 molar HCl and sodium hydroxide, and measures an initial temperature of 24.5 degrees Celsius for each solution. Then the student pours the two solutions into an insulated cup, stirs the mixture, covers the cup, and records a maximum temperature of 29.9 degrees Celsius. Is the experimental design sufficient to determine the enthalpy of reaction to a precision of 2 significant figures? Justify your answer. Now, this is a question that is really, really annoying because it makes sure you know what sig figs are used for. The thing to remember is that when you are doing an experiment, if you want to have a certain level of precision, you've got to carry that many sig figs throughout the entire experiment. And if you use any instrument which does not allow you to keep that many sig figs, then you cannot claim your result to assert that number of sig figs that you calculated or used in your experiment. So in this particular example, since they used the beakers, which only have a precision of 10 mils, and 10 only has 1 sig fig in it, then you cannot, therefore, do your calculations up to 2 sig figs. You could only do it to 1 sig fig because of these beakers. Any instrument that you use is going to cause you to basically drop the number of sig figs you can have in your result. So this guy right here having 10 mils, a sig fig of just 1, therefore you're only going to have 1 sig fig in your result. Doesn't matter if you've got 29.9 here or 24.5 here or anything, or 1 molar NaOH over here. This instrument right here drops your sig figs down to 1. You cannot do it. Okay. Next question. List 2 specific changes to the experiment that will allow the student to determine the enthalpy of reaction to a precision of 3 sig figs. Explain. Now, when you're looking at this, you go, okay, why did you even use beakers to measure out your solutions? Why not use the graduated cylinders? You want to use the graduated cylinders. So if you have 0.1 mils and you're measuring 50 mils, okay, so that means when you measure out, if your precision is 0.1 mils, plus or minus 0.1 mils, and you measure 50, then your volume is 50.0, and 50.0 is 3 sig figs. So that gives you 3 sig figs in your calculations for the volume. And so everything else, 1 molar sodium hydroxide, and the temperatures have 3 sig figs. This is 1.00 molar. You therefore have 3 sig figs in your calculations. One second, I've got a little problem upstairs, I think. Okay, my daughter was crying and something was bothering her. I got her some goldfish and some water, and she's happier now. Okay, so the next question was, list 2 specific changes to the experiment that will allow the student to determine the enthalpy of reaction to a precision of 3 sig figs. Okay, so the first thing I said was to use the graduated cylinders instead of using the beakers. The next thing is to use, instead of the 1 molar sodium hydroxide and hydrochloric acid, the other thing you could do is you could use the 2 molar hydrochloric acid and sodium hydroxide. And you might think that may not be that big of a deal, but the thing with using those 2 things is you're going to increase the change in the temperature. And if you increase the change in the temperature, then you are going to have a wider difference, or wider change in the temperature. And therefore, with a greater change in the temperature, you're going to have a more a larger number, essentially, and if you have a larger number, then your sig figs are more reliable. Now, I'm taking this straight, that one straight from the AP test itself. I think that one doesn't make a lot of sense, because if you have a change in temperature, which is 3 sig figs here, is it 3 sig figs? I don't think it actually is. Let me see. Calculator, where'd you go? I found the calculator for me. Tell me. But 29.9 minus 29.9, 24.5. Can't do this in my head. Okay, so that's only 5.4. So if you have a 5.4 change in temperature, 5.4 degrees Celsius change in temperature, that's only 2 sig figs. So if you have a larger change in temperature overall, you might be able to have maybe like 30.5 degrees Celsius ending temperature. So that'll give you a potentially could have more sig figs. Therefore, you could have your change in temperature. I feel like I'm totally messing this up. If you have a larger change in temperature, then the final highest temperature is going to be bigger. Okay. And if it's bigger, then you might be able to have something where you have like maybe a change in temperature of 10.1 or something like that. And therefore you would have 3 sig figs. Again, that one's kind of, I feel like it's kind of goofy, but it is true. You could potentially have a larger change in temperature, and therefore have 3 sig figs in your calculation. So there you have it. Okay, next question. A second student is given 2 solutions, 75 mils of 1 molar HCl and 75 mils of 1 molar sodium hydroxide, each at 25 degrees Celsius. The student pours the solutions into an insulated cup, stirs the mixture, covers the cup, and records the maximum temperature in the solution. The student calculates the amount of heat involved in the experiment to be 4.1 kilojoules. Calculate the student's experimental value for the enthalpy of reaction. Okay, not too hard. So you have, remember, the enthalpy of reaction is essentially how much heat was produced by the reaction divided by the number of moles of reaction. Now in this case, the reaction is 1-to-1. You got HCl reacting with sodium hydroxide to make sodium chloride and water. It's a 1-to-1 reaction. So we just have to figure out which of these reactants is limiting. And since we have the same amount of each of them, neither one is limiting. So we're going to make 0.075 moles of reaction. It's a 1-to-1 reaction, therefore, and since neither one is limiting, you're going to have 0.075 moles of reaction occur. So we can divide 4.1 kilojoules by 0.075 moles, and you got to remember this is going to be an enthalpy that is exothermic. Why? Because remember, the temperature of the water increased. So it's going to be negative 4.1 kilojoules divided by 0.075, and negative 55 kilojoules per mole is your answer. Okay. Next question. The student assumes that the thermometer and the calorimeter do not absorb energy during the reaction. Does this assumption result in a calculated value of enthalpy of the reaction that is higher than, lower than, or the same as it would have been had the heat capacities of the thermometer and calorimeter been taken into account? Justify your answer. So think about this. If you don't take into account the thing holding the reaction and the thermometer basically being in the reaction, what's going to happen? Okay, if you have the thermometer in there, some of the heat of the reaction is absorbed by the thermometer, right? So there's some reaction heat that is missed, essentially. It's also lost because that heat goes into the calorimeter itself. It's in the cup. So we are not accounting for some of the lost heat in the reaction. Some of it's absorbed by the thermometer itself, and some of it is absorbed by the cup holding the reaction. So the calculated delta H will be lower in magnitude because some of that heat is lost to the surroundings, and we don't measure it. Therefore, the amount of the change in the value Q is lower than expected, or lower than it should be. We measured a lower value than reality really tells us. Is it the best we can do? Sure it is. It's the best we can do. But the delta H is lower than it really is. Okay, part 3 here. One assumption in interpreting the results of the experiment is that the reaction between HCl and sodium hydroxide goes to completion. Justify the validity of this assumption in terms of equilibrium constants for the reaction. This is a really weird question. And honestly, when I looked at it the first time many years ago, I was like, what? Here it is. Okay, so HCl and sodium hydroxide react together. What is the net ionic reaction of that? What is the net ionic reaction? It's H plus reacting with hydroxide to make water. Okay? Do we have any equilibrium constant for this reaction? We do. We do have an equilibrium constant for that reaction. It's the self-ionization of water. Okay? So we could take this net ionic reaction and think of it as hydronium reacting with hydroxide to make water. Okay? The reverse reaction where water is ionized, it ionizes itself, is this guy right here, which is the reverse of what I just showed you up here. Okay? What is the value of Kw? The value of Kw, the equilibrium constant for this reaction right here, is 1 times 10 to the negative 14th. The reverse of that reaction would be exactly what sodium hydroxide and HCl are doing. So the reverse of that would be 1 times 10 to the 14th, which would be extremely favorable. So that's how you explain this reaction goes to completion based on equilibrium constants. You say, okay, this reaction looks like the reverse of the self-ionization of water. The self-ionization of water has an ionization constant, or equilibrium constant, which is 1 times 10 to the negative 14th. So the reverse, which is what we're seeing in the reaction, is 1 times 10 to the positive 14th. The end. Goofy question, really goofy question. But at the same time, you gotta know your stuff. Okay, C, a third student calculates the value for the enthalpy of reaction that is significantly higher than the accepted value. Identify a specific error specific error in procedure made by the student that will result in a calculated value for the enthalpy of reaction is higher than the accepted value. And then this is vague statements like human error or incorrect calculations will not earn credit. Just like in class. So that kind of stuff does not count. Okay, so what is one reason why they could have had a delta H bigger than expected? Okay, let's look down here. So there's a couple different things you could say here. You could say the student may have misread the thermometer, resulting in a larger delta T, resulting in a larger Q. At the very end of the day, yeah, it's human error. But again, you have to say it in a way that makes sense to cause the Q value on the top of the equation to be bigger than normal. So that's one possibility. Another one would be the student might have used 2 molar reactants instead, and they thought that they're using the 1 molar solution. So the 2 molar solutions will cause a greater change in concentration. You'll also have a greater number of moles that are reacting, but if you have that value on the top, but you think it's lower, then you're going to cause Q to be bigger than it really is. Okay, next question. Let me go back to it. It says, explain how the error you identified in part C1 leads to a calculated value of enthalpy higher than expected. Okay, so they just kind of want you to show what happens. So this is essentially what they're talking about here, right? So the value Q, if it's greater than expected, that means the mass times the specific heat of the solution times the change in temperature if the change in temperature, right here, change in temperature is too large because you made a mistake in measurement or something like that, then Q is going to be bigger than it should be, and so delta H is going to be too big. They basically just want you to show that mathematically, what's going on there. Okay. Those are the big questions. You guys didn't have a question about number 3. I think we did that in class, so that's fine. Let's just go straight to number 5 here. I think I cut out number 4 for this practice test. Methamide, CH3NO3. is a liquid at 25 degrees Celsius. The complete Lewis dot structure for methanamide, I think that's how you say it, is shown below. In the molecule angle X is not 100 degrees. Estimate the observed angle. Justify your answer. Okay? So looking at the structure here, what do we have? We have 3 electron groups around this carbon, and we have no lone pairs. This is going to come back to VSEPR essentially. So what is the angle here? Well, it's 3 electron groups around that central carbon atom, no lone pairs. What's the best way those substituents from the carbon can separate? It's at 120 degrees angle. So it's going to be 120 degrees. You just basically base it on VSEPR theory. You got 3 electron groups. The best way to repel would be 120. So it's a trigonal planar shape. Part 2, in the molecule angle Y is not 90 degrees. Explain why in terms of electron domains, VSEPR model. So why here between the nitrogen, hydrogen, and the other hydrogen? Why is it not 90? Well, you've got how many electron groups around this nitrogen? 1, 2, 3, 4. One of them is a lone pair. So remember that when you have 4 electron groups around a central atom, you're going to have that tetrahedral shape. And so tetrahedral has an angle of 109.5. That's something to remember. And if you have an electron group there that is lone pair, that's going to cause repulsion to squish these bonding electrons a little bit closer to each other because of the repulsion between the bonding electrons and the lone pair. So it's going to be a little bit less than 109.5. Okay, that's the answer they want you to see. It's going to be a little bit less than 109.5, and just explain there are 4 electron domains around the nitrogen atom. 3 are bonding, 1 is lone pair, so the lone pair pushes the bonding away. Consider a molecule with the formula CH2O2. The structure of this molecule has a geometry around the carbon atom similar to the geometry around carbon and methylamide. In the box provided below, draw the complete Lewis dot structure for the molecule. This is really easy if you remember our basic rules, which is that carbon never has any lone pairs, oxygen always has 2 lone pairs on it, and then hydrogen can only ever have 2 electrons on it. So carbon in the very middle, a double bond to the oxygen, a single bond to the oxygen, then hydrogen's coming off of the oxygen and the carbon, and then we're done. And those rules will always apply for something that's not charged. Next question. Okay, the structures of a water molecule and a crystal of lithium chloride are represented above. A student prepares a 1 molar solution by dissolving 4.2 grams of lithium chloride in enough water to make 100 milliliters of solution. In the space provided below, show the interactions of the components of LiCl by making a drawing that represents the different particles present in the solution. Base the particles in your drawing on the particles shown in the representations above. Include only 1 formula unit of LiCl and no more than 10 molecules of water. Your drawing must include the following details. Identify the ions, symbol and charge, the arrangement and proper orientation of the particles in the solution. So this is a kind of an IMF kind of question. They want to know, do you know ion dipole interactions? So if LiCl goes into water, what's going to happen? LiCl is going to ionize. And if it ionizes, how is water going to surround it? It's going to surround it like this. Water's oxygen side, which has the partial negative charge, is going to orient itself towards the lithium ion. And the chloride ion is it's negatively charged, so the waters are going to The water's hydrogen sides, which are positively charged, are going to orient themselves towards the chlorine at the end. B, the tougher question. The student passes a direct current through the solution and observes that chlorine gas is produced at the anode. Identify the chemical species produced at the cathode and justify your answer using the information given in the table below. Okay, this one's really annoying because they have a distractor in here. They talk about that chlorine gas. The chlorine gas is being reduced because the chlorides there are being reduced to chlorine gas, and they don't give you that in this box here. So the chlorine gas thing is completely a distractor thing. They want to know, well, what's happening if we pass a current through this right here? Well, it's happening, right? Okay, it's happening. The reaction is occurring. So that means that if we have the lithium ion doing something to cause the current to occur, the reaction to occur, then what do you have to do? You have to have the standard potential's got to be positive, right? So for the reaction to occur, E cell must be greater than 0 volts. This right here, the reduction of lithium ions is negative 3.05 volts. So lithium ions cannot be reduced. Okay, so something that's occurring in this solution right here must be the lithium. There must be lithium solid being oxidized. That's the only way it could occur. You'd have to flip this sign. It's too large of a number. Okay, so what's happening? Well, that must mean that lithium solid is somehow in there and it's being oxidized to Li+, and this right here, the water is being reduced to H2 gas and hydroxide ions, and that's the only way this can occur. The chlorine thing is completely a distractor question. So they basically are asking, well, how can I set these two half-cell reactions so that it is spontaneous? Well, it's got to be a positive voltage, so this has got to be an oxidation reaction. So lithium solid's got to be in there being oxidized, and then water's got to be reduced at the end. So what's at the cathode? H2 gas and hydroxide at the cathode, and then lithium was at the anode. Last question. Okay, we've got this reaction occurring with HIN, which is some kind of indicator with water in its equilibrium with its conjugate base IN- at H3O+. The indicator HIN is a weak acid with a pKa value of 5. It reacts with water as represented in the equation above. Consider the two beakers below. Each beaker has a layer of colorless oil, a non-polar solvent, that's important, on top of a layer of aqueous buffer solution. In beaker X, the pH of the buffer solution is 3, and in beaker Y, the pH of the buffer solution is 7. A small amount of HIN is placed in both beakers. The mixtures are stirred well, and the oil and water layers are allowed to separate. What is the predominant form of HIN in the aqueous buffer in beaker Y? The acid form or the conjugate base? The acid form or the conjugate base form? Explain your reasoning. Okay. This thing has a pKa of 5. Okay. Remember the indicators, their pKa's are basically a value telling you that if the pH were that number, it will shift in color depending on what direction you're going. So for this indicator, it has a pKa of 5. So if the pH of the solution is less than 5, then it's going to be yellow. If the pH is greater than 5, then the conjugate base form is going to predominate, and so it's going to be blue. Okay? So what is the predominant form of HIN in the aqueous buffer in beaker Y? The acid form or the conjugate base form? So since the pH of Y is 7, and that 7 is greater than 5, so this means the pKa is less than the pH, okay? So 5 is less than 7. HIN will therefore, in a pH of 7, ionize to form IN- and also produce H3O+. So at a pH of 7, the pKa is 5, so the indicator is going to shift to the right side, and it's going to produce IN- because the pH is greater than the pKa. Okay? B. In beaker X, the oil layer is yellow, whereas in beaker Y, the oil layer is colorless. Explain these observations in both acid-base equilibria, and interparticle forces. Okay, so in beaker X we have a pH of 3. Okay, in beaker X the oil layer is yellow. Okay, the oil layer is yellow. It should be it's colorless originally. Okay, so if it's yellow, that means that HIN's got to be in the oil. Okay, and then whereas in beaker Y the oil layer is colorless. Okay, so the oil in beaker X is yellow, which means the HIN has got to be in there, and then it's colorless in beaker Y, so that means the IN minus can't be in there because it's blue. Okay, so this is what I said in beaker X. The pKa is greater than the pH. The pH is 3, okay, and the pK is 5. So in the beaker X, the HIN form is going to predominate. Okay, and so since the yellow form of HIN is going to be there in beaker X, we can say, okay, that means the yellow is going to be there in that beaker. But why is it in the oil? The best way to explain this is to say that HIN is an uncharged compound. It has no charge, and so therefore it's going to be better capable of dissolving in the oil because it doesn't have charge. Oils are uncharged and they're nonpolar, so HIN must be nonpolar as well, and therefore be able to mix in with it using only dispersion forces. And then over here, the oil is colorless because IN minus is a charged compound, and if it's charged, then it's not going to be able to be dissolved in the nonpolar oil. It's only going to be able to dissolve in the water, the buffer solution. So therefore, it's not going to get into the oil because the oil is nonpolar. IN minus is charged. There's going to be unfavorable interactions between those two compounds. Okay, and I believe that is it. This is a 36-minute video. All right, hopefully this helps. There is a 2017 international test to practice on this week as well. Keep studying. If you have any questions, let me know. I'm happy to help you out. And with that, have a great week. And maybe I'll see you on Thursday if you want to do some office hours with me. And if not, that's totally fine too. I'm ready to help out no matter what. Have a great day. Bye.